안녕하세요 여러분. 오늘은 미방강식의 기하학적인 해법과 미방강식의 응용으로서 우리가 어떤 문제를 해결할 수 있는지에 대해서 살펴볼 예정입니다. 일반적으로 미방강식의 해를 구한다는 것은 상당히 어렵다고 했습니다. 따라서 수학자들은 정확한 해를 구하지 못하더라도 근사적인 해를 구할 수 있는 방법은 없겠느냐에 대해서 공부하게 되었고, 그러한 연구의 결과로서 제시된 몇 가지 방법 중에서 비교적 쉬운 경우에 대해서 한번 살펴볼 예정입니다. From now on, we will study how to get an approximate solution to a given differential equation. In general, it's very difficult to solve a differential equation, and so we try to get some approximate solution for the given differential equation. In particular, if we consider a differential equation of this form, y prime equal f of x, y, then as the derivative of y means the slope of the tangent line at the curve, by drawing some line segment at some point whose slope is f of xy, then we can get some kind of field which is called direction field or slope field. The line segment indicates the direction of a solution curve. We will see more in detail in a concrete example as following. If y prime is given in this form, so let's consider this part is large f xy. Then we want to find the direction field, and in the second step we want to sketch a solution curve which passes through the origin. By putting some numbers, for example, if x is minus 2 and y is 2, then we can see y prime is 3, and if x is minus 2 and y is 1, then we can also see that it is 4, and so on. In this way, we can compose a table for x, y, and its slope y prime. Then, based on such a table, we can draw a field like this one. For example, if x and y is 0, 0, then y prime is minus 1. So we draw a small line segment whose slope is minus 1. In this way, we can draw some field which is a field with some needles. And such a field is called direction field. And to draw a solution curve, we connect naturally so that it seems to be a lead curve like this one. By naturally connecting the curve which passes 0,0, then we may get a curve like this one, and this may be a solution curve for the given differential equation. But this is not always correct, so we should be careful that it's not the exact solution for the given differential equation. And Euler's method is a method to find the solution curve by considering some step size. Let's consider x0 is given and h is some positive number which is called a step size. Of course, h can be negative, but usually we think h as a positive number, and let x1 be obtained from x0 by adding h, and x2 is obtained from x1 by adding h, and so on. Then h is called the step size, and we can observe the following, that if y, which is a function of x, is a solution, then the solution curve is approximately the curve joining the line segment in the direction field. So, for example, assume that here is the exact solution curve, and assume that the curve passes x0, y0, and h is the step size, and so x1 is obtained from x0 by adding h, and the slope of the tangent line at this point is f of x0, y0, and so we can see that y1 is obtained by adding h at x0, y0 to y0. So because the tangent line of the slope means the ratio between this side and this side, we have such a kind of an equation. Inductively, we may get similar equation like this one. So following this step repeatedly, we can see such a kind of curve, and actually the solution curve and the approximate curve by joining P0, P1, P2 and so on is a little bit different, but we can expect that the curve obtained by joining P0, P1, P2 and so on may be similar to the solution curve. And this is called the Euler method to find the solution to a differential equation. You may observe that if h is almost 0, then the solution may be much more near to the exact solution. For example, if we consider such a simple case, if y prime is given as x plus y, and it has an initial condition y0 is 1, then first we construct a table for the solution curve, and with the step size h is 0.1. We just follow the formula. You should be careful to remember that yn is given as yn minus 1 plus h times n2 xn minus 1 yn minus 1. Just remember this formula, and xn is given as x0 plus n times of h, as xn forms an arithmetic sequence. As a step size, h is 0.1 and x0 is 0, we can see that xn is given as 0.1 times of n, and just by using this formula, and you can get a figure like this one just by calculation. So this is an example of application of the Euler method. And then from now on, we consider some example of applications in real life problem. So we assume that there is an island, and here lives rabbits. Rabbits are living in this island, and as the island has a limited space, the population of rabbits cannot increase infinitely. Let the population of rabbits at time t be denoted by p of t, and large k be the maximum number of p that the environment of the island can sustain. Then k is called the carrying capacity. We may assume that if the population is greater than k, then the number of rabbits will be decreased. So dp over dt would be negative. Based on this observation, we have a model for the population of rabbits given in this form, so that dp over dt is given as k times of p multiplied by 1 minus p over k. And this is called a logistic differential equation. And small k and large k can be some constants, and large k is called carrying capacity. And this is separable differential equation, and so you can easily solve this differential equation. The solution can be given in this form, where by putting t to be 0, a is given as k minus p0 over p0. So let's consider the differential equation. After observing the following note, if we have such a kind of logistic differential equation, and p over t is 0 or k, then dp over dt must be the right hand side is 0, and so it has a constant solution, and it is called an equilibrium solution. And you can see that the carrying capacity is infinite, then dp over dt is equal to k times p. So if in the island there are infinitely much grasses or rabbits to eat, then dp over dt can be increased proportional to p, and so we have a model like this one. But if the number of rabbits is almost k, then it is a very stable condition, and so the number of rabbits may not be increased or decreased. So dp over dt may be approximately 0. So you can see that the model for the number of rabbits is natural, and then we consider how to get this theorem. And by putting t equals 0, you can see that p0 equals 1 plus a k over 1 plus a. So you can see that p0 times 1 plus a equals k, and so you can see that a is k minus p0 over p0. Okay, so this part is naturally obtained by replacing t with 0. And so how to get this solution? Let this equation be star, then from star we can get a differential equation and so you should be careful that small k and large k are considered as constants. Just p and t are variables, and so we have an equation of and integrating both sides we have an equation like this one. Since this part can be given as right, this is equal to Rn minus this can be, do I need some mistakes? Oh. And so we can say that this is given as minus p. And by using this equation, you can easily show that Pt can be given in this form. Okay. So we have some application of separable differential equation to solve to predict the number of rabbits in some isolated island. And now we consider another system, which is called the predator-prey system. So in this case, we assume that rabbits and wolves are living in an isolated island, and depending on the number of rabbits and wolves, the number of these two species may differ. So, that here is an island, and watching that rabbits and wolves are living in the island, and the number of rabbits at time t is given as RT, and number of wolves time t is given as omega t. Then we can see that if the number of wolves is approximately 0, then the number of rabbits will be changed following this formula, and if conversely the number of rabbits is 0, then the number of wolves will be decreased proportional to this. So we have an equation of this form where small k and large this should be changed with r. Here k and r are assumed to be positive constants. We have such observation, and we may also see that the number of rabbits and wolves depends on the number of meetings between rabbits and wolves. So there may be some interaction between rabbits and wolves whenever they live, and the number of meetings may be proportional to the number of rabbits and the number of wolves. So we can see that this model will be slightly modified if the number of rabbits and the number of wolves are non-zero. Actually, we may naturally consider a system of differential equation of this form, So this equation is modified as minus 8 times of r omega because the number of levels will be decreased. And here A is assumed to be some positive constant, and the number of ulvas will be changed following this equation. The number of ulvas will be increased depending on the number of meeting between Levitch and ulvas, and so we have these two differential equations. Such a kind of differential equation is called the predator-prey system, or Volterra equation, Volterra equation. And so let's denote the differential equation. Here, KA or B are assumed to be some positive constants, and this equation is called the predator-prey equation, or Volterra equation. Actually, we may not solve such a kind of differential equation exactly, but we may get some approximate solution as following. For example, in this example, we assume that A is 0.001 and B is 0.0002 and K is 0.08 and R is 0.02. And the time is measured in months, and we want to find the constant solution. The constant solutions are called equilibrium solution, and we want to express the ratio for d omega and dr in terms of the number of Levitch and ulvas. And the third problem, we want to sketch a direct field in the r omega plane, and in this case we assume that the number of Levitch and ulvas are assumed to be 1040 at some time. Then we want to find some solution for this equation, and in this case we may sketch the curve for the number of Levitch and ulvas. Let's see step by step for this problem. So just replacing A, B, K, R in this equation, we have an equation like this one, and we want to find the constant solution. For some constant solution, the derivative of R with respect to T and the derivative of omega with respect to T should be 0. And so by replacing this part and this part with 0, you can get a solution like this one. And so this is the suitable number of Levitch and ulvas to live in the island. And if R and omega are 1080 respectively, then we may expect that there are no change in the numbers of Levitch and ulvas. And in the second problem, we want to find the derivative of omega with respect to R. And we have not studied this part, but later we will study parametric curves, and for parametric curves, how to differentiate and integrate. So we just accept this result, which will appear later. Anyway, if we adopt this one as a pet, then we have an equation like this one. And from the given condition, this condition and this condition, we have an equation like this one. And in this, based on this equation, this axis is denotes R and this axis denotes omega, and we can get a direction field like this one, and by connecting the segments appearing in this direction field, we have approximate solution like this one, and this is a phase portrait of the system. And in particular, if we assume that at some time the number of rabbits is 1,000 and the number of urgus is 40, then we have a point like this one. And in the above figure, we get a curve like this one, which is denoted as here. And the number of rabbits and the number of urgus will be changed following this direction. So if the number of rabbits increases, then the number of urgus are also increased to this point. But after arriving this point, the number of rabbits decreased, but the number of urgus are increased, and so we have a curve like this one. And at some time, the number of urgus will be decreased, and the number of rabbits are also decreased. So we have a curve like this one. And from this point to this point, the number of urgus are decreased while the number of rabbits are increases. So we have a curve like this one. This is the solution curve for the number of rabbits and urgus. So if we express the number of rabbits and number of urgus for time parameter, we may get two curves for the number of rabbits and urgus like this one. By using the predator-prey system, we may expect the number of rabbits and urgus. Okay. So we have studied differentiations of order 1 and two kinds of solution for differentiations of order 1. One is a separable differentiation, and the other is a linear differentiation. For linear differentiation, we use integrating factor, and we also have studied how to draw also a trajectory as an application of a separable differentiation, and to solve some real world problems. So we have considered the predator-prey system and the logistic differentiation. Okay, and this is a logistic differentiation, and this is a predator-prey system. And so we have studied everything that is needed to study in this semester for differentiation. 네, 오늘 강의는 여기서 마치도록 하겠습니다. 이렇게 해서 일단 미방강식에 대한 이론적인 부분은 여러분들이 다 공부를 했습니다. 네, 문제를 좀 더 풀어볼 필요가 있겠고요. 이걸 마치고 나면은 여러분들이 파라메트릭 커브, 폴라 커브에 대해서 아마 공부하게 될 겁니다. 그리고 급수에 대해서 공부를 하게 됩니다. 네, 수고했습니다. 마치겠습니다.